Hello students, I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today in this class we will discuss on space representation using the phase variables. In this class we will discuss on the phase variable form, the method of decomposition, the direct decomposition of transfer function, the cascade decomposition, parallel decomposition with the examples and the reference and MCQ questions. So what is phase variable? The phase variables are actually defined as the particular state variables which can be obtained from one of the system variables and its time derivatives. So usually the system variables is used in the system output and the remaining variables are in the derivatives of the output. Now first we will find out the state space representation from the transfer function. So when a state model of a linear time invariant control system can be represented by mainly three forms. One is the physical variable form, another is phase variable form, and final one is the canonical variable form. Now the state space representation in canonical form, which is also classified in the controllable canonical form, observable canonical form, diagonal canonical form, and the Jordan canonical form, we have already discussed the physical variable form and the canonical variable form in the other videos. So here we will consider the phase variable form. Now the system variable used is the system output and the remaining variables then used as the derivatives of the output. Now the phase variables provide a powerful method of state variable formulation. Now the disadvantage of phase variable formulation is the phase variables in general which are not the physical variables of the system, so they are not available for the measurement and control purpose. Now a link is provided between the transfer function approach and time domain approach while designing the control system. So during the designing implementation of the control system, it makes the process become easy and the straightforward. So let us consider the phase variable form. Now a linear time invariant single input single output system can be described by the transfer function in the given form. The GS equal to beta 0 s to the power m plus beta 1 s to the power m minus 1 plus beta m and s to the power n plus a1 s to the power n minus 1 up to a, where this alpha and beta may be the real constant scalar factor. Now we can consider one transfer function like this form, where Rs is the Laplace transform of the input and Cs is the Laplace transform of the output. So if we consider this transfer function, then we can find out the phase variable form and the equivalent block diagram from the given phase variable form. So here we can see the transfer function Cs divided by Rs that is equal to 24 divided by s to the power 3 plus 9s square plus 26s plus 24. Now the highest power of this denominator is 3. That indicates this is a third order system and there will be 3 state variables as well as 3 integrators. So we have assigned the state variables in this way, that y is equal to x1 and x1 has been received from the integration of x1 dot, which is equal to x2, and integration of x3 gives us the result x2. That means x2 dot is equal to x3 and x3 dot is equal to, from this equation if we cross multiply this, cs by rs equal to 24 by s cube plus 9s square plus 26s plus 24, then we find out that x3 dot is equal to 24 into r minus 9 into x3 minus 26 into x2 minus 24 into x1. So that's why this minus 9, minus 26 and minus 24, which are actually the coefficients of the denominator, has been used as the feedback, and the feedback signs are the negative feedback. So this one is representing the block diagram which shows the phase variables. Is the decomposition technique. Now we know that the linear system can be modeled by differential equation, transfer functions or the dynamic equations. Now all these methods are closely related to each other. Now the state diagram forms a close relationship among the state equations, computer simulation and the transfer function. So the decomposition method is defined as the process of obtaining the state model from the given transfer function. So we can decompose the transfer function using 3 different ways. So these 3 basic methods of decomposition of transfer functions are the direct decomposition, cascade or series decomposition and the parallel decomposition. Now all of these 3 schemes of decomposition has its own merits and it is best suited for the particular purpose. So let us discuss on these 3 basic methods of decomposition. First one is the direct decomposition of the transfer function. So direct decomposition is applied to an input-output transfer function which is not factored for. So we can see for an example here, ys by us equal to 5s square plus 6s plus 8 divided by s to the power 3 plus 3s square plus 7s plus 9. So this transfer function is not in the factored form. So we can use the direct decomposition method of this representation of the state equations. Now the advantage of this method is that it is a general method and it can be applied to any system. The resultant matrix, that is the system matrix, will be in the Bush form. So here one thing we have to remember, that we have to divide both numerator and the denominator by the highest power of the s, and then we can draw the state diagram and the state model from the given system. So we can assign the state variables in the following way, that is x1 dot become x2 and x2 dot is equal to x3 and x3 dot that is equal to 9 x1 minus 7 into x2 minus 3 into x3 plus u, and the output y that is equal to 8 into x1 plus 6 into x2 plus 5 into x3. So first we can write the state equations and then we can find out the vector matrix form. So from using these 3 equations we can write down that x1 dot, x2 dot and x3 dot that is equal to the system matrix A, which is coefficient of x1 dot is equal to x2. That means coefficient of x2 is 1 over here and the remaining will be 0. So that's why the first row is 0, 1, 0. For the second one, x2 dot, that is equal to x3. That means only the coefficient of x3 will be 1 and the remaining 2 will be 0. So it is 0, 0 and 1. In the same way, the terms of u are also 0. And x3 dot, the coefficient of x1 is equal to -9, coefficient of x2 is equal to -7, and coefficient of x3 is equal to -3, and coefficient of u is equal to 1. That's why the last row is -9, -7 and -3, and coefficient of u is 1 over here. So the system matrix become in the bush form or the companion form, and that is 0, 1, 0, 0, 0, 1 minus the coefficient of the denominator part, that is -9, -7 and -3. Similarly, we can find out the system matrix A, B. In the same way, we can find out the C matrix. So for the C matrix, we can find out that coefficient of x1 is 8, coefficient of x2 is equal to 6, and coefficient of x3 is equal to 5. And there is no u term, so the D matrix will be is equal to 0. So this is the direct decomposition method of the transfer function, which can be applied for the transfer function which is not in the factored form. So next is the cascade decomposition. The cascade decomposition method is applied to the transfer functions that are written as products of simple first order or the second order components. Then the state diagram is drawn for each section, and the complete state diagram is obtained by combining in the series the state diagram for each section. Now the advantage of cascade decomposition is the poles and zeros of the transfer function appear as isolated branch gains on the system diagram. So the study of the effect of system becomes easier when the poles and zeros has been varied. So let us take one example for the cascade decomposition. So here we can see that the transfer function is in the factorized form, and it can be factored as 1 by s plus 2 into 1 by s plus 3 into 1 by s plus 4. So now we can see that the state diagram has been obtained for each state diagram, and then we have combined it serially. So if we consider the term ys by us in the way y by x1 into x1 by x2 into x2 by u, then for each single term we will get the state diagram, and then the overall state diagram will be the combination of this each block. So this is very much advantageous, and if the poles and zeros of the system has been varied, we can easily study the effect of the system of these changed poles and zeros. Next is the parallel decomposition. Now if the transfer function is in general form, it can be also written as in the partial fraction form or in the plus form. So plus means parallel over here. So this parallel decomposition method is based on the partial fraction approach, and steps which are used to make the parallel decomposition, we will first expand the transfer function by the partial fraction method, and the expansion consists of the first order terms. Then we will draw the state diagram of each factor separately. Then the complete state diagram of the system can be drawn by adding the parallel combination of the state diagram of each of the first order terms obtained in the partial fraction expansion. That means for this type of decomposition, we will draw the state diagram of this d1 by s1 plus lambda, then d2 by s plus lambda 2, then d3 by s plus lambda 3 like this, and then we will merge by the parallel combination of the state diagram which we have obtained in the partial fraction expansion. Next, we will select the output of the integrators as the state variable, and then we can write the dynamic equations of the system. So let us take example parallel decomposition. Here we can see the transfer function is given as s plus 5 by s square plus 10s plus 9. So using the partial fraction method, we can write down in the addition form, that is half divided by s plus 9, and the remaining one is half divided by s plus 1. So now we can draw the state diagram of each term, that is first one is half divided by s plus 9 and second one is half divided by s plus 1. So if we draw the state diagram of half of s plus 9, that means output by input equal to half divided by s plus 9. So here we have assumed it x1 dot, and the integration of x1 dot becomes x1, and the feedback is minus 9. So we can write x1 dot is equal to u minus of 9 into x1 into this half, that means this half is gain. Similarly, for the second one we can draw x2 dot, and this state after integration it gives us x2, which is the another state variable, and feedback is minus of 1. So x2 dot is equal to u minus of x2, and again here also the gain is half, so half is multiplied over here, and the overall output is the summation of these two. So the overall output is the summation of the two different inputs. So from this state diagram we can write down the state equation, and the output equation becomes half of x1 plus half of x2. So in this way we can draw the state model, and x1 dot and x2 dot becomes minus 9 into x1 plus u, that is 1 over here, and another is x2 dot is equal to minus 1 into x2 plus u. So this one is the parallel decomposition method. These are my references. I hope after this video lecture you have a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture. So you are requested to go through it gradually and solve the questions by your own. The answers are attached at the end of each question.